And we're back. Welcome back from your weekend. Today we will pick up with a continuation of inference, specifically method of moments estimation, a little help from mom, so to speak, and then we will have an example. Okay, so this material is based on Chapter 9 in the Barron book, Probability and Statistics for Computer Scientists. So when we talked about moments, we talked about method of moments as being an approach where you can solve for good estimators or come up with good estimators. And if you do so, follow this procedure of equating the population moment with the sample moment, or so-called empirical moments, you can be guaranteed that the estimator that you get, function over data, will have certain stability properties for unbiasedness and consistency. And so we had the case population moment, that is mu sub k. Let me select my pen here. Today I will do blue pen color. So we have the case population moment that is noted as mu sub k, where k talks about the exponent. And this is the expectation of your random variable exponentiated to the kth power, and that's the same k as the subscript here, mu sub k. And so if we were to write an expression for this, okay, well, expanding what expectation means, it's the ith sample exponentiated to the kth power, and this is a typo. We don't have the probability of x to the k. It's just the probability of x. Okay, and so it's the weighted average, or the mean, or expectation as it is, of this random sample from some distribution exponentiated to the k power. And so we have the analog of the population moment. This population moment is computed where this expectation is associated with the probability associated with the population. And we have the analog here from the sample version, the case sample moment. And so this case sample moment is noted m sub k, right? So that k, again, also represents the exponent. And here we have 1 over n times the sum of each of these samples exponentiated to the kth power. And if you think about it, if the probability of each one of these samples, if each sample is equiprobable, that means the probability is 1 over n. So you can imagine p of xi here, that should be capital X, is nothing more than 1 over n. So it's similar in behavior as the population moment. In this assumption, because it has a summation, it's a discrete distribution, countably infinite, but we could certainly substitute this summation would have an integral if it were a continuous distribution. But nonetheless, this is the case sample moment, so m sub k is 1 upon n, the sum of each one of our samples exponentiated to the kth power. And with this, we can actually create estimators that we want to stand in place, and these estimates, mu sub k, are going to be from some samples. So we have a set of sample points. And so the first sample moment is the sample mean, and we showed that before. So now let's take a look at some other moments. The case central population moment, where k is greater than or equal to 2. So let's describe this expression, mu sub k, and because it's centralized, we're subtracting off from each example, we're subtracting off from each data point, we're subtracting the center, right? And that has the effect, well, we talked about it last time, of shifting your distribution so that instead of your distribution being centered over the so-called center of mass, mu, it's now centered, if we write the new version of it, it shifts it to the left, and it shifts it such that it's centered about origin. So mu, the center, is going to be equal to origin. And mu, the mean, is just mu sub 1. Okay, so we have the expectation of each measurement subtracted from its mean, and we're going to take this and we're going to exponentiate to the kth power. Now in this notation, you can imagine here some square brackets where we're squaring the difference between each measurement and the center, and we're taking that difference and we're raising it to the k power, where this k is the same as the k for that index. And so if we expand this out by our definition of what expectation is for a population parameters, using our population, Well, the population is governed by some probability, and so we have the sum of this difference, xi minus mu1 raised to the k power, and we're going to take the weighted sum times probability of that particular measurement xi. And it's a random variable, so we use big xi. We do that. That's our second. If we talked about the second population central moment, this k would be 2. And you get something that looks like the variance. And so the k sample central moment, if we were to look at the sample version of the central moment, okay, well, that's m prime sub k, right, because it's centralized, 1 over n. So it's like having equal probability for each of these data points. The probability is equiprobable for each one. And we have our sum, data point, each one xi minus the center. And since we're talking about the sample central moment, if we centralize it based on the samples, we subtract off the center, which is x bar, our sample mean. And we exponentiate that to the k power. Okay, so that's almost like saying the variance, assuming that we have these data points are equiprobable. And so the idea then is we're going to use or calculate, we hope, an estimator that's for mu k, the k population moment, and we're trying to estimate or compute an estimator for mu k from the sample. So what we did then, well, what did we do? We looked at method of moments estimation, and we look at a distribution that we feel will best model the problem that we have at hand. And we notice how many parameters, k, that this distribution has. And so if a distribution has one parameter, like the Poisson, we're going to estimate or compute an estimator for one estimator, because we want that one estimator to stand in place of that one parameter. If we have two parameters, we're going to compute an estimator for the first one and the second one. And so in order to estimate or come up with estimators for k many parameters, what we're going to do is we're going to take the first k population moments, where k is equal to 1, 2, 3, and so forth, and we're going to equate them with the first k sample moments. So that means if we have the first population moment, we're going to equate that with the first sample moment. If we have a second population moment, we're going to equate that with the second sample moment. Now, how do we know whether we use 1 or 2? Well, if your distribution, x, is distributed as some distribution, and if that distribution has a parameter, let's say theta 1, then you're going to just equate mu1 to m1 for that distribution. If it has two parameters, excuse me, if it has two parameters, theta 1 and theta 2, then we're going to equate the first population moment with the first sample moment, and then we're also going to equate the second population moment, mu2, with the second sample moment. So then the result of solving this equation, once you equate it, you're now going to solve for the unknown and come up with an estimator that you're going to use to stand in place of this mu1. In this case, you're going to solve for an estimator that's going to stand in place for mu2. So you're going to get some stand in place mu1, let's call it mu1 hat, and you're going to have some estimator that's going to stand in place of mu2, let's call that mu2 hat. Okay, so the example we had before is that you observe some number of events, and these events occur during some number of windows of observation. And so we talked about this. Here's your window of observation, delta t, and the only requirement is that your windows of observation have to be the same size. So delta t could be 1 second, could be 5 seconds, could be 15 minutes, and so forth. So you have windows of observation of the same size, and you see events that occur where these circles represent the events. So during the first window of observations, you see 2 events occur, then maybe next time you see 3 events occur, and then you see maybe 1 event occur, and then maybe you see 4 events occur, right? So you believe from this description, and let's say these events were customers that arrived into a retail establishment, for example, you think, gosh, well, what distribution best describes this? And you say, aha, maybe it's a Poisson, and you'd be right, but you still have to make a decision for your model if you're trying to ask questions and mimic this so that you can now test and get answers to various questions. So you assume it's Poisson, so X is distributed as Poisson, and Poisson has a single parameter, and that single parameter, let's just call it theta, or you could just call it lambda. We know that from last semester. You could also say you have some parameter theta, call that theta 1, and you don't know what estimator, you don't know what the true lambda is governing all of the observations you have for that particular establishment. So you get some samples. These are the observations from something like an overhead camera over the entry box for your store, for your retail establishment. And then you enterprise to compute some statistic that you can use to substitute, so some function over the data that you can use as a substitute that will stand in place of this unknown parameter. And so following this method of moments estimation approach, you know you only have one parameter. There it is, lambda, or more correctly, theta 1. So what do? You take the first population moment, mu sub 1, as defined from the previous slide, and you equate that with m1, the first sample moment, and then you equate the two together and then solve for the unknown. So mu1, that's just the expectation with respect to x, and you equate that with m1, which is just x bar. Okay, so you say E of x is equal to x bar. What is E of x, or the expectation of a Poisson random variable? That's just lambda. So this gives us lambda is equal to x bar. So there's your result. If you want an estimator for lambda, you just compute your x bar, where x bar is just the sum, 1 over n. I goes from 1 to n, where n is the number of samples, of xi, right? That's going to be our x bar. And so this x bar is something you compute over data. This is a statistic, and we arrived upon this statistic using method of moments estimation, and therefore this x bar is a great replacement for lambda. And so because it's a great replacement for lambda, we're going to now write hat over our lambda. So we're going to write this lambda hat to connote that this particular statistic is going to be a good replacement for our lambda. So we say lambda hat, where hat indicates estimator. So this is a so-called method of moments, or MME estimator for lambda. Now, how we would write method of moments estimator for lambda is we would say lambda hat. So that means it's an estimator for lambda. So hat means estimator, and we'd pronounce this estimator for lambda, and then we'd say MME, corresponding to the fact that we arrived upon this estimator hat for lambda using method of moments estimation. Okay, so this is, in a nutshell, a high-level review of what we talked about last time. Okay, so let's continue on with method of moments, and we're going to use an example to discuss, or a more sophisticated example of a case where we have more than one parameter associated with our method, with our distribution of interest. And so we had this problem in the past, and it talks about the effectiveness of a processor. And so we have a bunch of processing times, and there's a utility in command line Unix called top. And if you run top, it'll give you a screen full that looks like this on the command line. And what it gives you is the amount of CPU time that your processes on your computer have taken. And so CPU time corresponds to the amount of cumulative time, total time, that a process, program and execution, has run on the CPU. And so let's define S, our sample, as being 30 randomly selected jobs or processes or programs in execution. And so here we have 3 rows of 10. So there's 10, 20, 30, and these numbers represent the CPU time. It could be in seconds, could be in minutes. It doesn't matter really what the units are. So nonetheless, we have these 30 samples where each one represents the CPU time for a process running on your system. So the first thing we want to do, let's assume that we don't know what distribution we should use to model this. Well, we could compute a frequency histogram. Okay, and then we get this characteristic shape. And if we look at this envelope, we say, oh gosh, well, we have a peak here, and it kind of tails out on the end here, tails to the right. If we calculate or transform this frequency histogram into a relative frequency histogram, we essentially multiply each one of the bin counts by the total number of data points. So we would take this 1 and we divide it by 30. So we multiply by 1 over 30. We get this number here, 1/30th. Likewise here, this is 5. We divide that by 30, multiply by 1 over 30, and so forth. And so here we get a relative frequency histogram, which looks exactly like the probability distribution. And this dotted line is the envelope describing the general shape of this particular distribution. So this is a histogram and relative frequency histogram. And the shape of this distribution looks very gamma-like, right? And I'm also using the structure of the problem, the fact that you have some number of times, 30 many of these time samples. It looks just like a gamma distribution. And if we recall, a gamma distribution is a sequence of alpha many steps, each taking some time, where the time is described by an exponential distribution. So effectively, we have an exponential distribution giving us 30 different time measurements. Now, of course, alpha in this case will be 30 if we go to the previous slide, because we have 30 many measurements, 30 many time samples. So this looks very gamma-like. And we can think of alpha as the number of processes whose runtime was measured. Okay, so let's take a look at this gamma distribution. The gamma distribution from last semester is used to describe so-called multi-stage execution. Now, here we say X is distributed as gamma, where this alpha refers to the number of stages, and in this case, alpha is equal to 30 for our example, because it's 30 measurements, and this lambda, that is the parameter that governs the exponential. Because remember, when we talk about an exponential distribution, that exponential distribution has a parameter lambda. Okay, so this is the probability density function, and this is a density function because the gamma distribution traffics in time, right? And time is real valued. It's drawn from some value on the real number line. So it's continuous distribution, and continuous distributions have density functions. And so the density function of a gamma distribution, f of x, where x is the time observed, is equal to lambda to the alpha power upon gamma of a, of alpha, that should be alpha, lambda to the alpha power, gamma of alpha, times x to the alpha minus 1 e to the minus lambda x. And of course, x is assumed, because time is always non-zero, it's assumed to be greater than 0. Well, time could be 0, but if time is 0 here, then you don't have any time between, any phase takes 0 time, which means that the phase didn't run, right? So x is assumed to be greater than 0. And so here, the gamma function, if you use a positive integer, it's just that integer minus 1 factorial. So if you input alpha, or a, gamma of a is a minus 1 quantity factorial. Otherwise, if you input a real value, it's the following integral between 0 and infinity, x to the a minus 1 e to the minus x dx. But because this gamma deals with stages that are positive integers, we're only concerned for this about this version of the gamma function. And of course, it's called the gamma distribution because it derives its name or gets its name from the fact that it has this gamma function. Okay, so when we compute the first moment of the gamma, well, that's just e of x, because remember the formula for moments, we said mu sub k is equal to e of x to the k power, right? And so you do that, k is 1, so e of x to the 1 power. Well, we did that before for the gamma. You could also certainly look that up. That's alpha upon lambda, where lambda is the parameter representing the time component, and alpha is the component representing the number of stages. Likewise, the second moment, now this is the central moment, the second central, so this is central for the gamma distribution, right, is going to be the variance of x, and if you do that out, that's just E of x minus mu, where mu is mu1, quantity squared, right? And so we did that out before last semester. You can also look that up. That's just alpha upon lambda squared. Okay, so we have the first moment, and then we also have the second central moment. Now, why do we have the first and the second moment? Well, because we have two parameters for the gamma. This is the first parameter, that's our alpha, and the second parameter is lambda. And because we have two parameters, we're going to need two sets of equations, or two equations rather, for our method of moments, because we need an estimator for the first parameter, and we also need an estimator for the second parameter. So if you have two parameters, you look at the first moment and the second moment, equating the first population moment with the first sample moment, and likewise the second population moment with the second sample moment. Now, one of the questions is, when we take that second moment, do we use the second moment or the second central moment? You could try both, and if you can't solve, then you chose the wrong one. Okay, so we model this problem, this set of times representing processes, as a multi-stage execution, so that fits with the gamma, and the gamma is governed by two parameters, so it has a two-parameter model where the first parameter is alpha and the second parameter is lambda. Now, I don't know, and maybe you could try to make a guess, but nobody knows what the true parameters are for the gamma distribution governing the samples that you receive for 30 processes running on your system. If you know, then maybe you should buy a lottery ticket because you are very, very lucky. But nonetheless, it's a two-parameter model, and because we don't know what the true parameters are governing the population that describes or gives you values that you measure, the best you can do is to substitute an estimator, let's call that theta 1, for our first parameter, and a second estimator, theta 2, for our second parameter that just happens to be lambda. So what do? We first compute the first sample moment, because what we want to do is equate the population moment with the sample moment, so we need to compute what those moments are. So let's start with the first sample moment, and that first sample moment, k is equal to 1 in this case, but we look at the formula arbitrarily for the arbitrary kth sample moment. So m sub k is equal to 1 upon n. We have our sum from 1 to n of xi to the k power. Likewise, because we have a second parameter, that lambda, we're going to look at the second sample moment, and we're going to consider the second sample central moment. Okay. Now, if you didn't do the central moment, you just do the second sample moment, and when you tried to solve, things wouldn't work out, so you know you chose wrong. So we're going to use the second sample central moment, the centralized version of the second moment. So we have the first moment and the second moment, but for the second moment, we're considering the second central moment. So the k sample central moment, that general formula, m sub k prime is equal to 1 upon n, the sum of these differences between each sample measurement and the first sample moment, which is also m1, right? So this m1 is nothing more than x bar, and we raise that to the kth power. Okay, so let's fill this in from our data. So we have our actual measurements, our samples, and this one says we compute x bar from all those samples, and again, those samples are a couple slides ago. Here are our samples. We have 30 of them. So this would be our x1 sample. That would be our x2 ... and this last one would be our x30, right? So when we compute our first sample moment, what we're doing then is just computing this x bar, where these xi's raised to the 1 power, because it's mu k m sub 1, those xi's are just your examples of samples that you're given, your measurements, your actual measurements for your job CPU times. Okay, so if we do that, we get this result, 48.6 0.2 and change. And then if we look at the second sample central moment, the case central sample moment is as follows. This is the equation. M is you have 1 over n, sum xi minus x bar to the 1 to the 2 power, right? So it looks a lot like variance. Now, if you look at this in the book on page 240, s squared is not the same as big S squared. Big S squared is this quantity that we're calculating, but S squared is unbiased, and the difference is we have this leading quantity is 1 over n minus 1 when we compute S squared. That's the sample variance, and it's unbiased, and I'll let you look that up as to why you need that 1 over n minus 1. Okay, so this m2 squared, if you calculate that, that's 679 and change. Okay, so we just computed the first sample moment and the second sample central moment. So now let's look at mu1 and mu2. Well, from the gamma distribution, oops, I just jumped ahead a slide. From the gamma distribution, we know mu1 is equal to alpha upon lambda. Mu2 is equal to alpha upon lambda squared. Now, we computed here for our sample moment, our first one, x bar is equal to 48 and change, and here m2 prime is equal to 679 and change. So we have that. So we're going to equate our first population moment, mu1, with our first sample moment, m1. So we have our m1, okay, we know what our mu1 is, but let's just write the equations that we use. Now, this first equation, that's going to take care of our first parameter. We're going to call our first parameter theta 1, and we're going to call our second parameter theta 2. Theta 1 is alpha, theta 2 is lambda. So this is going to take care of our first parameter, theta 1, and then this next one is going to take care of our second parameter, theta 2. Okay, so let's try this. So now, all right, well, if we do this, we'll substitute for what our population moments are. So now this equation, we're going to substitute for what mu1 is. Mu1 here, we just said, is alpha upon lambda. Mu2 here, as we just said, is alpha upon lambda squared. So we have a system of two equations. We have alpha upon lambda is equal to m1. We have alpha upon lambda squared is equal to m2 prime. Okay. So now that we've filled in or substituted for what mu1 is and what mu2 is, and we got that from last semester, we talked about the first and second moments, or the mean and the variance, or rather the mean and the variance rather of the gamma distribution, right? Well, we just make that substitution. Okay. So now we're going to substitute for m1 and m2 prime. Okay. But because we have two equations, we're going to do a little bit of algebra, and we're going to substitute because we're going to use a result from this first equation in the second equation, right? Because here we have lambda, we can isolate this lambda, and we plug that into the second equation to give ourselves a solution. So if we do this, okay, well, we can multiply both sides of equality by lambda. So if we multiply both sides of equality by lambda, well, we get alpha over lambda, and we have equals m1. So we multiply both sides by lambda, so we say times lambda, and we say times lambda. So lambda in the numerator denominator, that cancels out, that goes to 1, and we're left with alpha is equal to m1 times lambda. So now we're going to divide both sides of equality by m1. So we say 1 over m1 on the left-hand side. We say 1 over m1 on the right-hand side. So m1 in the numerator denominator cancels. That goes to 1. And we're left with lambda is equal to alpha over m1. Okay, great. So now we can take this expression for lambda that we have as our result from the first equation, and we can substitute that in this lambda squared term, right? So we substitute lambda here. So if we say lambda squared, that would be alpha squared over m1 squared. We can make that substitution in the second equation. So if we do that, and we do a little bit of math, well, what does that give us? Well, we started out with lambda equals alpha over m1. So if we had alpha for the second equation over lambda squared is equal to m2 prime, well, we substitute this alpha over m1 for a lambda squared. So that gives us, we have alpha over, and we said alpha squared over m1 squared is equal to m2 prime. So here we have, in the denominator, we have this alpha squared over m1 squared. Okay, well, this will stay in the denominator, and this one, if you have 1 over something, that's going to come up here in the numerator. So we're left with m1 squared times alpha over alpha squared is equal to m2 prime. Okay, so now if we have this m1 squared alpha in the numerator over alpha squared in the denominator on the left-hand side of equality, and we have m2 prime on the right-hand side of equality, that's how we get this step. Okay, so now we can cancel one copy of alpha in the numerator and one copy of alpha in the denominator, right? That leaves us with 1 here and alpha instead of alpha squared in the denominator. So the result of this is going to be that we're going to have this equation. All right, so let's see where that comes from. So if we take this expression, we get m1 squared, alpha, copy of alpha here, and alpha here, cancels. So we have m1 squared over alpha is equal to m2 prime. So now we can actually solve for alpha. We multiply both sides of equality by alpha. So we say times alpha. These cancel, goes to 1. And then we divide both sides by m2 prime. So that gives us m1 squared over m2 prime is equal to alpha. So that's our expression for alpha. This is going to be an estimator for alpha, the parameter of the gamma distribution. And because it's an estimator, we call it alpha hat. And that's exactly what we get. So we say alpha hat is equal to m1 squared over m2 prime. Now, each of these m's, these are the sample version of the moments, the square of the first sample moment, and this is the central version of the centralized version of the second sample moment. Okay, so that's our alpha. Now that we know what our alpha is, we can now go back to the first equation and make that substitution. So if we make that substitution, right, we have alpha here. We substitute for that, so we say m1 squared over m2 prime over m1 is equal to lambda. So what does that mean? Well, that's like saying m1 squared over m2 prime times 1 over m1 is equal to lambda. So you have m1 here in the denominator, you have m1 squared. So one copy of this cancels to 1. So you're left with m1 over m2 prime is equal to lambda. And that's our other estimator. Because it's an estimator, you call it lambda hat. So with this, we get lambda hat. The estimator for lambda is going to be m1 over m2 prime. And alpha hat, the estimator for alpha, is going to be m1 squared over m2 prime. And so here we have our two equations, and we set this up, these two equations, by equating the first sample, moment, population moment, with the second, we get this by equating the first population moment with the first sample moment, and then we have another equation in our system of equations by equating the second central population moment with the second central sample moment. And we do that, we get two equations, and then we solve for the unknowns. Okay. So it just so happens then this lambda hat is computed over samples from the data, and this alpha hat is also computed from samples on the data, so we can literally substitute this lambda hat for the lambda and this alpha hat for the alpha. So once we get those values, we get our samples, our measurements, we compute M1, we compute M2 prime, and we calculate in this fashion what our lambda prime would be and what our alpha prime would be. And then we just substitute for that gamma, and now using something like MATLAB, we can sample from it, and it will mimic the CPU process measurements that we had. And you can now ask questions about it, like the average CPU time, or pretend that you're sampling from your CPU and then think about how long some computation might take, for example. Okay, so we equate them, the population moments with the sample moments, and then we solve. Sometimes we have to substitute, getting a system of equations, and we arrive upon the answer. The results are stable estimators. Okay? All right. So given M1, right, we said M1 X bar, we knew what that value was. M2 prime, we knew what that value was, 679 and change. So now we can actually find values for lambda hat and alpha hat, right? Well, lambda hat is M1 over M2 prime. So if we divide 48 and change by the 679 change, we get 3.4 and change. And then alpha hat is M1 squared over M2. So that's M1 squared over M2. M1 squared over M2 is 0.07 and change. So here we have alpha, and we also have our lambda. Okay, so for method of moments estimation, following the prescription for how we arrive upon these stable estimators, you think long and hard about the problem that you have. So then, once you've done that, you think again and select a distribution whose model assumptions fit for the problem that you have. Does the shape of that distribution make sense based on what you have? You could try a histogram to visualize it, but you analyze what distribution and come upon an answer, what distribution best models the scenario at hand. Okay, so then once you've arrived upon that distribution, you will use to model the problem that you're given. You count the number k of parameters for that distribution that you've selected. Okay. In the case of a gamma, it has two parameters, so k equals 2. In the case of a Gaussian or normal distribution, it has two parameters. In the case of a Poisson, it only has one parameter. Nonetheless, you count k the number of parameters. So then you compute the first k population moments. You compute the first k sample moments or empirical moments, and then you equate them with one another. You equate the population moments with the empirical moments and solve for the parameters just as we have done. So now once you have that, you have your estimators and you're done. So the key takeaway from this is, yes, absolutely, you literally match moments. You match the population version of the moment with the sample version of the moment for as many moments as you have parameters for that distribution that best models your problem. If you cannot solve for some desired parameter, try another moment. So for example, if you did not choose the central version of the moment, then maybe you select if you did not try the central version of the moment, then try the non-central version. If you try the central version and it didn't work when you tried to solve for the desired parameters, try the central version. Okay, so choose another moment if you can't solve for the desired parameter. Okay. So that's method of moments estimation. But method of moments estimation is not the only game in town. Method of moments estimation is just one approach. Now there's another competing approach, or I shouldn't say competing, is another approach called max likelihood estimation. And so we're going to jump into max likelihood estimation. It's another way of arriving upon estimators that are stable substitutes for the unknown population parameters. So let's take a look. So I'm going to set up a scenario. Let me go back to my pen here. Okay. So I'm going to set up a scenario. So we're going to talk about a shop, a coffee shop. Agent 007, James Bond, has retired from the British clandestine service. Not satisfied with the typical retirement, our international man of mystery has decided to open a shop, a coffee shop. but he needs help with mathematical modeling in order to optimize his caffeinated concern to achieve fiscal success. So here's our hero, Mr. Bond, and like any small business owner, he does everything in his coffee shop. He makes the coffee, he busses the tables, he's everywhere. But using his special spy skills, nothing escapes his attention. So someone comes in at some period of time, delta T, 15 minutes, and he sees a customer at the front counter. There's one person who's arrived. He notes that down, makes a mental note. Then in the next time instant, 15-minute block of time, he sees 2 people, 3 people come to the counter. He makes a mental note. So this keeps happening time after time after time, every 15-minute block of time. Mr. Bond sees, say, 15 minutes later, sees 4 people come to the shop. So in the first time instant, saw 1 person. In the second time instant, saw 3 people. In some other time instant, next time instant after that, he sees 4 people come into the shop. So that coming into the shop is an event, and that event had a count representing the number of people who arrived in the coffee shop. So Mr. Bond needs some help. How do I model this? Well, you might think, gosh, is it Poisson? Well, it exhibits a lot of properties of Poisson. We have a standard unit of time, delta T, is 15 minutes. We had first person in first block of time, window or module of observation. We had 3 people in the next one, 4 people in yet another one. So you believe it's Poisson distribution. So if your measurement, your sample, the number of people that arrive at the coffee shop, then you know that a Poisson has just one parameter. It's a 1-parameter model, and that parameter is lambda. Now, in fact, you could tinker with the Poisson distribution, and this is an example for different settings for lambda. Lambda is the rate parameter. If lambda is 1, it looks more mushed to the left. If lambda is 2, it kind of flattens down a little bit. Lambda is 3, 4, etc. So as you increase lambda, well, that hump, that place where you have a lot of probability, it mushes down and kind of pushes to the right, right? So you see here lambda is 9. It looks very normal or Gaussian-like. But it started out being mushed to the left, and it got more and more flat as it pushed down and moved to the right a little bit. Okay, so Poisson seems like a very good choice because this deals with quantities that occur in time, events in time. And we know Poisson is a very good model for that. Okay, so you assume it's Poisson, you think and believe in your heart it's Poisson, but the problem is you don't know what lambda to choose because you have no idea about what is the true lambda that governs the arrival rate of customers for units of time for your coffee shop. Well, what are you going to do? You're going to make a substitution. You're going to find an estimator that you're going to use to stand in place of this population lambda, and you hope that this estimator, let's call this estimator lambda hat. Let me turn on the pen. You hope that this estimator, this statistic, this function over the data, would be a good replacement, and you're going to use that lambda hat, that replacement, as a substitute for this unknown population parameter, lambda. So if you're going to choose some replacement, why not choose some lambda value that best describes the data that you've seen, this data that you've measured from, say, Mr. Bond? Okay. So lambda is distributed as Poisson, and we're going to examine more in detail what this idea of best describes the data means. So you have a probability mass function for the Poisson. Now this Poisson traffics in numbers of events, x, right? So x is the input to the mass function. It's a mass function because the Poisson traffics in counts. So this is a discrete probability distribution, and we talk about mass functions when we refer to discrete probability distributions. So this input, this probability, says what is the probability that I observe x many events, where an event in our case refers to the number of people that come into the coffee shop in each unit of time delta t of 15 minutes. Now, of course, delta t can be whatever you want. Depending on your model, you choose what makes sense for the system that you're studying. Okay, so we have our mass function, and this Poisson also has a parameter. It has a single parameter. Now, we'd write it sometimes x is distributed as Poisson with a single parameter lambda, so it's a one-parameter model, a one-parameter model. So if we're going to find a substitute, that means we need to take the first population moment and the first sample moment, and we're going to equate the two and solve. Okay. Now, sometimes when we write the mass function, we acknowledge the fact that the parameter is lambda for the Poisson, but we acknowledge that using the semicolon. So we could say for the gamma, p of x, and we'd say semicolon, alpha, and lambda, where sometimes when we write the mass function, an alternative way you'll see it in the literature being written is to write the parameter, the input to the mass function, right? That's the quantity, the measurement, whose probability you're testing with this distribution, first likelihood. And then you have the governing parameters, the population parameters for the distribution. So for the Poisson, you'd write probability of x, and you'd say indexed by parameter lambda. Here for the gamma, this is the gamma distribution, which is a continuous distribution. You'd say probability of x a time, and this probability distribution is indexed by these two parameters, alpha and lambda. So here we write the mass function, probability mass function for the Poisson distribution, and this mass function, it reads the probability of some number of events, and it's indexed by unknown population parameter lambda. So this is the mass function. It's lambda to the x power, e to the minus lambda upon x factorial. Okay, and we studied that last semester. So here we have a mass function, and we have this mass function for all of our observations. And so for the first observation, we observe one person. For the second observation, we observe 3 people. And for that last observation, we observed 4 people. So this idea of best describes the data means that we're going to now evaluate this mass function, p of x, on each one of the data points that we observe. Okay, so let's do that. So we substitute for x as one person, 1. We write p of 1 indexed by lambda. So we just substitute here. That's lambda to the 1 power, e to the minus lambda over 1 factorial. For the next observation, we evaluate that mass function on this observation. So we have p of 3 indexed by lambda. So that's lambda to the 3, e to the minus lambda upon 3 factorial. And then we do the same for that last observation, p of 4 indexed by lambda, lambda to the 4 power, e to the minus lambda over 4 factorial. Now, of course, if we had some other measurements, we would do this for every single sample, right? So if we had another observation here, let's say it was 2 people, we'd evaluate p of 2 indexed by lambda, right? So we do this for every sample we have. If you have 100 samples, it would be 100 evaluations. I'm just showing you these 3, okay? All right, so now, of course, if we want to know this idea or measure this idea of best describes, it's really, really important. We're going to select parameters lambda that best describe the data that we have. We observe and we evaluate the mass function on those observations, and then we can put them together. So let's see how we put them together over our entire data set. So we have our observations X. There's the first observation, the second, the third, the fourth, the fifth, and so forth. And for each observation, we have a probability, or sometimes it's called a likelihood. So we said P of X1 lambda is X1, right? That was one person. And then we had 3 people and 4 people. So we had, for the first observation, we evaluated the mass function. For the second observation, we evaluated the mass function. We do that for each of the n many observations. We evaluate the mass function using that nth observation, each one of these observations. First one, second one, third one, up to and including the nth one, if you have n many samples, right? So we do that, and then this idea about best describing the data, what it is, it describes the parameter lambda, because we have that single lambda here, that's the same lambda. We want to find the parameter lambda that leads to the largest likelihood evaluation of the mass function over every single observation we have. So that value for lambda will be the lambda such that we get the best description of the data. We're maximizing the sets of likelihoods, which is why this is called the max likelihood estimation approach. So best describes the data means that we have some unknown parameter lambda we're solving for that leads to the largest likelihoods over all of the observations. So this idea over all of the observations, well, we have this mass function evaluated in the first observation, on the second, third, fourth, up to including the nth observation. What does it mean to say over all the observations? Well, we're going to multiply, right? And so here, where that comes from is that we have some number of observations, and we want the joint probability. Now, of course, these samples, they're independent. And if you want a set of independent samples, you want the probability associated with all of them, some sequence of observations, well, because they're independent, you're going to multiply, right? So what does that mean? It says that if each of the xi, or samples, is independent and identically distributed, that means each of these is independent. So going back to first principles, the probability of joint distribution is just the probability of the marginal distribution. So probability of x1 times probability of x2 ... times the probability of that nth measurement. So what does that say? It says that if you want the probability of the entire sequence of independent identically distributed samples, or likelihood as we said on the previous slide, the probability of the jointly of the entire set of samples taking on certain values given your lambda is going to be that probability for the same lambda for this one multiplied with the probability for the second one, probability for the third one. Now you notice it's the same lambda for each one of these. It's the same lambda here, same lambda here. So once you set a lambda, lambda is the same for all of these. And we can compute the probability of these examples jointly by multiplying together the probabilities of each one of these separately, as long as these measurements are independent and identically distributed. So we assume the observations are IID samples, and then the probability of this joint occurrence of observations is nothing more than the product of the individual observations. So we have the probability of x1 up to and including x2 is equal to the superproduct, I goes from 1 to n, of probability of each one of them. So now what we're going to do is select a parameter that maximizes the so-called product of the marginal likelihoods. Now, this is a little bit messy. Yes, I can agree, because this is a pretty messy expression. So what we're going to do then, we're going to clean this up a little bit. We don't want it to be so messy. We want it to be a nice, comfortable expression. It's going to be a little bit difficult to have the product of a set of things and find the lambda that's going to maximize that product. Okay, so we start out, we have some observations. We take the mass function evaluated on each of those observations, and we're going to multiply them together. And when we multiply them together, we get that superproduct expression. So the product of probabilities of a single observation, each one of these is the marginal. So we have the marginal probability or likelihood associated with the first observation, the marginal likelihood associated with the second observation, and likewise with the nth observation, the marginal or likelihood. So we multiply together all of these marginals, or the one at a time probabilities of each one of these samples, using the same distribution with the same parameter lambda. Okay, and so this idea of best describes the data means that the probability or the version of the Poisson or the setting of the lambda associated with a Poisson that best describes the data is that lambda that maximizes the value of the product of each one of these marginals. Okay? Because this is a probability it's going to be between 0 and 1. This is a probability it's going to be between 0 and 1. They're all probabilities that are going to be between 0 and 1. So you want to choose a lambda such that the product of each one of these individual terms, when you take the product, the result is the largest value it could take on. And that's the so-called max likelihood estimator. The version of lambda, the estimator, that maximizes this expression. Okay? All right. So the joint distribution is the product of the marginals, right? The basic facts and probability we talked about last semester. So we want to select the parameter lambda that maximizes the product of the so-called marginal likelihoods. This is called the joint likelihood or probability, and this is called the marginal because it involves a single sample or single variable. Okay, so let's take a little bit of a detour here. Now, we don't like this expression. It's very messy. So what we're going to do is we're going to make a transformation. And this transformation that we can make will clean up this expression. And we want to maximize it. So there's some lambda where this expression is going to take on a maximum value. Now, of course, for that version of lambda where it achieves its maximum, we don't want to do damage to that, but we want to clean up this math through some transformations so that we preserve what that maximum is. So we're going to use a class or draw from a class of transformations or functions that can perform on this messy expression to make it a much cleaner, neater, easier to work with expression and still preserve where that maximum occurs. Okay? And so a so-called monotonic transformation is defined as a type of transformation that preserves the relative ordering of the terms of interest. So let's say we have the following set of numbers, 1, 3, 7, 12. We know if we order these values, we have 1 is less than 3, it's less than 7, it's less than 12. They come in this order, 1, 3, 7, 12. Let's say we were to compute a transformation. And this transformation is going to say, I'm going to take every value and I'm going to multiply by 2, times 2. If I multiply by 2, let me rewrite this. 1 less than 3, less than 7, less than 12. So if we multiply by 2, this first term, 1, becomes 2. The second term, 3 times 2, becomes 6. This next term becomes 14. And this next term becomes 24. Now, of course, let me order this and say this is the first value, this is the second value, this is the third value in my sequence, and this is the fourth value. Now, if I were to look here, this is the same as 1 times 2. This is the same as 3 times 2. This is the same as 7 times 2. And this is the same as 12 times 2. Now, of course, the first term that we had, when we apply this times 2 transformation, the position or ordering did not change. The first value, okay, it's now 2, but it didn't move. It didn't all of a sudden become greater than the second quantity in the second position. So if we multiply by 2 and the relative position or order of the term, the first term didn't change in its relative position relative to the others, that's a so-called monotonic transformation. So multiplication by some quantity is by positive quantity is a monotonic transformation, right? In this case, well, multiplication in general is a monotonic transformation. If we take the natural log, okay, natural log is also a monotonic transformation. Now, if we say ln of 1, ln of 1, if we say natural log ln of 3, if we say ln of 7, and we say the natural log ln of 12, well, the ordering has not changed, right? It's still the same ordering. Now, the values might have changed, but we still have the first quantity. There it is. We still have the second quantity. There it is. We still have the third quantity. There it is. We still have the fourth quantity. There it is. So the relative position has not changed if we transform each one with this log, so therefore logarithm is a monotonic transformation. So why does it matter? So let's say we were trying to do an optimization and we're trying to find the value where it achieves its maximum. So in this particular case, the value where it achieves its maximum, if our, let's say, f of x is equal to x squared. So where does f of x equals x squared, where does it achieve its value? Well, if we, all right, let's see, that's 1, that is 9, that is 49, and this is 144. Okay, it achieves its value, maximum value at that fourth position. So if we were to take this f of x, and if we were to take that and we multiply it by 2, where does it achieve its maximum? Okay, if we multiply it by 2, guess what? It still achieves its maximum at that fourth position, because that would be 144 times 2. That would be 49 times 2, 9 times 2, 1 times 2. The maximum is still the same position. If we took the natural log, and so we said natural log of f of x, where does that achieve its value, right? So we said the natural log of x squared. Well, natural log of 1, right? Natural log of 1 squared, which is 1, is here. So we have ln of 1. This would be ln of 9. This would be natural log ln of 49. And lastly, this would be natural log ln of 144. Now, of course, if we took the natural log of this function x squared, ln of x squared, well, and we ask the question, where does that achieve its maximum value? It's still the quantity in the fourth position. So 2 is a monotonic transformation, natural log is a monotonic transformation. And so because we want to find where this expression achieves its maximum, as long as we transform it with a so-called monotonic transformation, the quantity that maximizes it does not change. It's the same position. Okay? All right. So monotonic transformations preserve relative ordering. And therefore, if we want to know which lambda is the lambda where this expression achieves its maximum for some value of lambda, we can take a monotonic transformation of this expression and see where that transformed version, for what version of lambda, where it achieves its maximum, and it's still the same lambda, okay, because of this monotonicity property, preserving the relative ordering. Okay, so what are we going to do? We're going to take this expression, and the monotonic transformation we will apply is going to be the natural log. So we'll take the natural log of this side, if we said ln of the left-hand side of equality, that's the same as the natural log ln of the right-hand side of equality. So if we take the natural log of a product, that turns into a sum. So that would be the sum of ln of the first term times the second term, third term, so forth. So with the natural log, if you take the natural log of things multiplied together, so if we said ln of A times B, that's the same as ln of A plus ln of B, right? So our product turns into a sum, and we have the sum of the ln of each term that was originally involved in that product. So now we have the sum for I goes from 1 to n of ln probability of each xi. Okay, so let's now, we select the parameter. If we take this monotonic transformation, now instead of selecting the parameter lambda that maximizes this product, we're now finding the parameter lambda that maximizes this sum. Okay, and so we could describe this as being selecting the parameter that maximizes the sum, instead of the product, of the log marginal likelihood. These are marginal likelihoods instead of a joint likelihood. That's the joint, that's the marginal. And now we're saying the log of the marginal likelihood. And it's the sum of the log marginal likelihoods instead of the product of the marginal likelihoods. This is the product of the marginal likelihood. This is the joint likelihood. And this is the sum of the marginal likelihoods. Okay. And of course, it's the same lambda that maximizes this expression is also the same lambda that maximizes this expression because this transformation is monotonic. Okay. So we take that expression, the sum of the log marginal likelihoods, and we recall what our probability was. So this probability, our likelihood, we have the product of two things in the numerator. So, and we have the product, and we have x factorial in the denominator. Now we're going to use the fact that the log of a over b is equal to the log of a minus the log of b. We're going to use that along with the fact that the log of a times b is equal to the log of a plus the log of b. We also have a property where the natural log of a to the b power is equal to b times the log of a, right? Okay, so we have these properties and we're going to substitute them and see what we get. So what we get the log of p of x, where p of x is lambda to the x power e to the minus lambda over x factorial. That's going to be minus lambda plus x ln lambda minus ln of x factorial. So where does that come from? Okay, well, if we have ln of lambda to the x power e to the minus lambda over x factorial. What is that? That is the log of something over something else. That's going to equal ln of lambda to the x e to the minus lambda minus ln of x factorial. Okay, so if we take this first term, well, there's our minus ln of x factorial. We look at this first term, and that first term is the product of two things. It's this lambda to the x power and e to the minus lambda. So if we expand that, we say ln of lambda to the x power plus ln of e to the minus lambda power, and then we still carry down this expression minus ln of x factorial. Okay, so now, well, we're not quite done yet. We have this lambda to the x power. Well, we use the identity before. That's x times ln of lambda. Okay, that is ln, natural log of e to the minus lambda. Well, if you take the natural log of e to anything, that's just whatever that exponent was. So that's minus lambda. And then we have minus ln of x factorial. So we rearrange terms. So we put this over to the right. So that's minus lambda plus x ln of lambda minus ln of x factorial. Okay, so with that, if we take the natural log for the probability mass function of the Poisson distribution, we get this minus lambda plus x ln lambda minus ln x factorial. So we can replace this term, the log marginal, with that term, minus lambda x ln lambda minus ln of x factorial. Okay, So if we do that, we're now substituting for the Poisson likelihood, and we're evaluating the logarithm of this. And we get that expression, as we said before in the previous slide. So what do we have? We have the sum. We take the log, monotonic transformation. We get the log marginal likelihood here underneath the sum. And we now substitute for what we just solved, and we get the sum for I goes from 1 to n of minus lambda plus xi ln lambda minus L natural log of xi factorial. Okay? All right. So now our problem of finding the maximum product of marginal likelihoods is now finding the maximum of the sum of these log marginal likelihoods, which is exactly this expression. Okay? This is the sum of the log marginal likelihoods. Okay. So now we want to find the lambda that maximizes this expression. So how are we going to do that? Okay. Well, let's take a little bit of a segue to talk about some terminology from optimization. In optimization, an objective refers to some goal or condition that you're trying to reach. So in mathematical observation, it's an expression or function. That's how you talk about an expression. And you're trying to find some unknown for which the function achieves either a minimum or a maximum. The expression is called an objective function, and the possible values that you can have, this unknown, these things you consider, say, oh, does it achieve a maximum here? Does it achieve a maximum there? Those are called feasible solutions. So you're trying to find a feasible solution where some objective function reaches a maximum or a minimum. And the process that you use to find the feasible solutions, that's called your optimization algorithm. So what does this mean? Well, your lambdas that you're trying, those are your feasible solutions. So you have a whole bunch of values for lambda. Lambda can be any number from real valued, right? It has to be greater than 0 because the rate can't be negative. You want to find some lambda that maximizes the expression. So this is going to be our objective, which is the sum of the log marginal likelihoods. And the feasible solutions are going to be all the values of lambda that you can try, right? So maybe lambda equals 0.37. Maybe lambda could be 1.5. Lambda could be 10,000, 100,000, 0.7 or so forth, right? So this is an optimization problem, and we're going to solve this optimization problem using a bunch of approaches. And once we solve it, that best lambda where this achieves its maximum, because it's a max likelihood estimation, that's going to be our lambda hat that we're going to use as the substitute. And so this idea of a good substitute is one, or estimator is one that maximizes the likelihood function over all of your data because it best describes the data that you have. Okay? All right. So this is our objective function. And now mathematically what we'd write is we want to find some argument, some version or some setting of lambda that maximizes this expression. So mathematically, and you'll see this in literature, we write argmax lambda that maximizes, so some argument we're calling lambda that maximizes this expression. That result we're going to call lambda hat. Okay, so what we'll do is end with this. Now, of course, I'm from Massachusetts, and you can't be from Massachusetts without a Kennedy reference. So and so, my students, for the good of your models, ask not what your lambda can do for you, rather ask what you can do for your lambda. So you will be searching for the best lambda that you can find. So we will end there. Stay tuned. On Thursday, we will finish this conversation.